Welcome to this video introducing you to vectors in math and its relationship to displacement in physics. Some of the prior knowledge that would be helpful would be vector between 2 points, geometric and algebraic operations on vectors, vector magnitude, and finally components of a vector. Let's start with some definitions. Position is often denoted by letter D with an arrow because it is a vector quantity. It's a location of an object with reference to a point, and we often use the coordinate system, the origin of it, for that point. Displacement is the change in position. The change is denoted by this triangle sign, which is delta, and position is just D with an arrow. Displacement or change in position between points A and B would be the position B minus position A. These are both vector quantities or kind of like position vectors. So all we do is we take the x and y component of position vector B and we subtract it by the x and y component of position vector A. Let's do a quick example in one dimension. We got a line here and our reference point here is this coordinate system, and we got position A, which is 5 meters to the left of the coordinate system, and position B, which is 25 meters to the right of the coordinate system. We're going to take right to be our positive, and position A is 5 meters to the left, therefore is negative 5 meters to the right. We can also write this as 5 meters to the left, and this makes sense. This position is 5 meters to the left of the coordinate system. For position B, it's located 25 meters to the right, so positive 25 meters to the right, or negative 25 meters to the left of the coordinate system. Let's look at the displacement from A to B. We're going to take right to be positive. The displacement is shown in the diagram, and the displacement is equal to position B minus position A. So to do this, we're going to take 25 minus negative 5, and those are the positions that's shown above, and we get 30 meters to the right as our final answer, and that makes sense. B is 30 meters to the right of position A. Now let's do the same example. This time position A and B are going to be exactly the same, but we're going to change our reference point. We're going to put it right in the middle, 15 meters from A and 15 meters from B. Now for the positions, this time we're going to take left to be positive just because we can, and position A is going to be 15 meters to the left, so this time it's going to be positive 15 meters to the left, or it's going to be negative 15 meters to the right because we took left to be our positive coordinate. For position B, it's located 15 meters to the right, so it's going to be negative 15 meters to the left or 15 meters to the right. Okay, now for the displacement, we're going to take left to be positive. It's still displacement or change in position from A to B. So we're going to take position B and subtract it by position A. Position B is negative 15 to the left, and position A is positive 15, so subtracting it by just 15, we get negative 30 meters to the left or 30 meters to the right. Now let's look at a two-dimensional situation here. We're going to have our coordinate system, and we're going to look at the displacement from A to B. We're going to take east and north to be positive. So position A has east and north components of 20 and 50, and position B has east and north components of 180 and 140 meters. To find the displacement from A to B, we need to subtract position A from position B. So position B is 180 and 140 for east and north, and position A has 20 and 50. So we subtract them to get 160 meters in east and 90 meters in north as our components of the displacement from A to B. If we look at it graphically, we have the displacement in the x direction or in the east direction as 160, and in the north direction or the y direction as 90 meters. In physics, it's also important for us to find the distance, which is the length of vector A to B, and the angle from east to north, or the angle that they've traveled from initial position to the final position. To find the length, we use the magnitude formula, so square root of the x component squared plus y component squared, which is approximately 184 meters. And to find the angle, we need to use SOHCAHTOA, so we're going to use tan theta is equal to the opposite side, which is the y component, divided by the adjacent side, which is the x component. So the opposite, or the y component, is 90, and the x component is 160, and theta is tan inverse of 90 over 160, and it's approximately 29.4 degrees. To write our final answer, we write it as displacement from A to B is approximately 184 meters. Direction starts from the east direction, and the angle moves towards the north. So it's east 29.4 degrees towards north. Now let's look at the idea of total displacement. Total displacement is the displacement from the initial position to the very final position. So it can be calculated by taking the final position and subtracting it from the initial position. If we don't have the initial and final position, the total displacement can also be calculated from the sum of all individual displacements. For example, let's imagine that we got a person who's traveling from position A to B, B to C, and C to D. The total displacement will be from the initial position A to the final position D. It can be calculated by displacement A to D is equal to position D minus position A, or it can be calculated by displacement A to D is equal to the displacement from A to B plus the displacement B to C plus the displacement C to D. The summary of this lesson is written here, but is fast forwarded, so if you want, you can pause the video and write down any information that you may need. And now we're going to look at a couple of examples. For the first example, we want to determine Robo's displacement if its initial position is 3 meters west and 5 meters north, and its final position is at 10 meters south and 4 meters east. We often start these questions with drawing a coordinate system and setting directions to be positive. In this case, we're going to choose east and north to be positive, but any direction would have been okay. Then we will write the positions. The initial position is 3 meters to the west. Since we chose an east to be positive, that means we're going to write -3 for that component, and it's 5 meters north. And since we've taken up to be positive, or north to be positive, then it is +5. For the final position, we have 4 meters to the east, that's same as our direction, so it's +4. And we have 10 meters south, which is opposite to our direction, so it's -10. To find the displacement from initial to final position, or the total displacement, we take the final position and subtract it by the initial. So we will subtract the components from each other, so 4 minus -3 is 7, and -10 minus 5 is -15 meters. And those are the components of our displacement. We do have the displacement in component form, but we do want to write it in another form with including the angle. So 7 meters to the east and 15 meters to the south, we will draw that out, and the displacement is from the initial point to the final point. To find the magnitude of the displacement, we will use the magnitude formula. That's the root of x component squared plus y component squared, giving us approximately 16.553. And to find the angle, we know it's a right angle triangle, so the opposite to theta is 15 and adjacent is 7, so tan theta is 15 over 7, giving us a theta angle of 64.98 degrees. To write our final solution, the displacement is approximately 16.6 meters, and we start from the east direction, and our angle goes towards the south direction. So it's east 65 degrees south to 3 significant figures. For our next question, we have Robo who travels 15 kilometers west, 40 degrees towards south, then 20 kilometers north, and then 25 kilometers south, 30 degrees towards east. And we want to determine Robo's displacement. In this question, because we don't have the initial and final position, we have to use the displacements instead. So the total displacement is the sum of all of the individual displacements. We're going to assume that Robo starts at some position A and it travels towards west, 40 degrees towards south. So we draw the angle towards south, and then we draw the components and we connect the two lines, and we know the magnitude of that is 15 kilometers. Let's label that point B, and we know the side adjacent to the 40 degrees is 15 cosine of 40, and the sides that is opposite is 15 sine 40. Robo then travels 20 kilometers north, so that's just from B to C, and the magnitude of that is 20 meters. And then Robo travels 25 kilometers south and then 30 degrees towards east. So we draw the angle, we draw the components, and we know the magnitude is 25 kilometers, and we're traveling from point C to D. The side adjacent to the angle is 25 cosine of 30, and the side opposite to the angle is 25 sine 30. Now we have broken down all of the displacements into their east and north components. We're going to draw a coordinate system, and we're going to label east and north as our positive coordinate axes. The total displacement in the x direction from A to D will equal to the displacement of A to B in the x direction plus displacement from B to C in the x direction plus the displacement from C to D in the x direction. The displacement from A to B is in the opposite direction to our positive coordinate system, so it's negative 15 cosine of 40. The displacement B to C is 0 in the x direction, and the displacement for the last trip C to D is 25 sine 30, and it's going in the same direction as our coordinate system, so it's positive. This will give us approximately 1.01 kilometers to the east. We will use the same idea in the y direction, so the total displacement in the y direction is displacement from A to B plus B to C plus C to D, all of them in the y directions. For A to B, it's the opposite direction to our positive, so it's going to be negative 15 sine 40. For B to C, it's in the same direction, so it's plus 20. And for the very last one, it's in the opposite direction, so it's negative 25 times cosine of 30. And they all add up to approximately 11.3 kilometers in the north direction. Note that after adding everything up, the directions that we get should correspond to the same direction as our coordinate system. Now that we have the x and y components of our vector, we're going to draw them out and we're going to combine them into one form. So we got the 1 kilometers to the east and we got the 11.3 kilometers to the south. And the final displacement will be from the initial position to the very final position. Now the angle is going to be tan theta is equal to the opposite over adjacent side. So in this case, 11.3 divided by 1, and we use the tan inverse to find the angle to be approximately 84.9 degrees. Now to find the magnitude, we will use Pythagorean theorem, so that's root of x squared component plus y squared component, and that when we add them, I'm using the exact values, and I will get approximately 11.3 kilometers as my final answer, and therefore the final displacement is 11.3 kilometers in the east direction and 84.9 degrees towards the south direction. I have left you with 2 questions, and I will try to post the solutions to these in a separate video as soon as I can. I hope that this video was helpful for you to get an understanding of the connection between displacement in physics and vectors in mathematics. Thank you for watching.